Hello there, and welcome to The Sleepy Scholar. Tonight's journey takes us down to the ocean floor, where wide plains, hidden mountains, deep trenches, and quiet vents shape one of Earth's least familiar places. We will explore how the seafloor forms, why sunlight disappears long before the deepest zones, and how life survives in pressure and darkness. If you enjoy these quiet explorations, consider subscribing so you can easily return here whenever you need to rest. For now, get comfortable. Let your eyes grow heavy. Let's begin. Beneath the waves, the ocean floor covers more of Earth than all the continents combined. Although people often imagine the seafloor as a flat, dark bottom, it is a huge landscape with slopes, plains, cliffs, valleys, volcanoes, and trenches. Most of it lies far below the reach of sunlight, where water pressure is strong and temperatures are usually cold. Because ships must usually pass over an area to map it in detail, large parts of the ocean floor still lack high-resolution coverage, even though broad global maps exist. This does not mean the seafloor is empty or simple. It is one of Earth's largest active systems, shaped by moving plates, falling sediment, underwater eruptions, and slow chemical exchange with seawater. Beneath the quiet surface of the ocean, the planet has a hidden ground of immense scale. Along the continents, shallow shelves continue the land beneath the sea. They usually begin at the coastline and stretch outward before the seabed drops more steeply into deeper water. These shelves can be broad and gentle, especially near low coastal plains, or narrow, where mountains stand close to the shore. Sunlight often reaches much of the water above them, making shelves some of the most productive parts of the ocean. Rivers may deliver sand, mud, and nutrients onto them, while waves and currents move material back and forth over long periods. During ice ages, when sea level was lower, many shelves were dry land or coastal plain. Their submerged surfaces can preserve old river channels, ancient shorelines, and traces of landscapes that once stood under open air. A shelf is the sea's quiet continuation of the continent. Beyond the shelf, the continental slope begins the long descent into deeper water. It is usually much steeper than the shelf, though it is still gentle compared with many mountains on land. Along this slope, sediment that gathered near the continent can slide, creep, or be carried downward by dense underwater flows. These movements help transfer material from coasts into the deep sea, where it may settle across fans and plains. The slope is important because it forms a boundary between the familiar margins of continents and the darker, wider floor beyond. Submarines, deep-diving vehicles, and sonar maps have revealed that these slopes are often cut by gullies, scarps, and channels. The continental slope shows that the edge of a continent is not a sharp line at the beach, but a long underwater descent. Cutting through many continental margins, submarine canyons carry the shape of valleys into the sea. Some begin near river mouths, while others form along slopes where sediment moves downward in powerful underwater flows. These canyons can be steep, winding, and surprisingly large, sometimes reaching from shallow shelves into deep basins. They help carry sand, mud, and organic material from land and shelf areas to the deep sea. Turbidity currents, which are dense mixtures of water and sediment, can rush through them and reshape the seafloor. Unlike river canyons on land, submarine canyons are hidden below water, but they can be just as dramatic in form. They are natural pathways linking coasts with the deep ocean floor, connecting mountain rain, river sediment, and abyssal plains. Their channels make the buried edge of a continent easier to imagine, even from far above. When sediment suddenly moves downslope, turbidity currents can behave like underwater avalanches. They begin when sediment becomes unstable on a slope and mixes with water, forming a dense flow that sinks and travels downhill. These currents can move quickly, carve channels, break undersea cables, and spread layers of sand and mud across deep basins. When the flow slows, heavier grains settle first, followed by finer particles, creating layered deposits called turbidites. Geologists study these layers to understand old seafloor events and the movement of sediment through ocean basins. Although a turbidity current may be brief, its deposit can remain in the rock record for millions of years. The deep ocean floor is shaped not only by quiet settling, but by sudden pulses of moving earth. A single flow can leave a wide, lasting sheet. At the foot of many slopes, submarine fans grow where sediment spreads into deep basins. They often receive material from submarine canyons and turbidity currents, which carry sand and mud from shallower regions into deep water. As the flow leaves a narrow channel and loses energy, it spreads across the basin floor and drops its load. Over many events, the deposits can build wide fan-shaped bodies with channels, levees, and layered sediment. Some submarine fans are among the largest sediment accumulations on Earth. They can preserve records of river systems, climate changes, sea level shifts, and slope failures in their layers. A submarine fan is a quiet meeting place between land and deep ocean. It is built by repeated journeys of sediment, carried downhill through darkness until the grains settle into broad, low forms. Across some basins, deep sea channels curve like rivers hidden underwater. They are not made by ordinary flowing rivers, but by dense sediment-laden currents moving downslope beneath the sea. These channels may have bends, natural levees, cut banks, and abandoned paths, showing that underwater flows can organize themselves into familiar patterns. Some channels stretch for hundreds or even thousands of kilometers across deep basins. They can guide sediment toward abyssal plains and help build submarine fans. Their shapes are known from sonar maps and sediment studies because the water above them hides the view. A deep sea channel shows that the ocean floor can have pathways, not just open surfaces. In the dark, mud and sand can travel along curving routes, leaving a calm record of motion after the flow is gone. Along those channels, levees build as fine sediment spills over the edges. As a turbidity current moves through a channel, its faster, denser core stays low, while finer suspended material may rise and spread outward. When that material settles, it builds raised ridges along the channel margins. Over repeated flows, these levees can become broad and high enough to shape the path of later currents. They are much like river levees in general form, though their building flows are hidden beneath deep water. Levees help scientists reconstruct how sediment moved through ancient basins, especially when old seafloor deposits become exposed as rock on land. A deep-sea levee is a patient ridge made by overflow. It marks the edge of a vanished current, giving shape to events that may have lasted only a short time. Farther from land, abyssal plains become some of the flattest and quietest landscapes on Earth. They spread across deep ocean basins, often thousands of meters below the surface, where sunlight never reaches the bottom. Their smoothness comes from fine sediment that slowly settles through the water and blankets rough volcanic crust beneath. Over long spans of time, tiny shells, clay, dust, and organic particles soften the shape of the seabed, filling low places like snow settling into hollows. These plains may look empty from a distance, but they hold delicate traces of deep-sea life, small tracks, burrows, and scattered animals adapted to darkness. The calm appearance of an abyssal plain is the result of countless slow arrivals from the water above, settling grain by grain. It is a landscape made by patience, depth, and steady silence. Across much of the deep basin floor, low abyssal hills give the seabed a gentle texture. They are small compared with great mountain ranges, but they spread widely across deep basins. Many form near mid-ocean ridges, where faulting and volcanic construction create rough crust before sediment slowly covers it. Over time, fine material softens their outlines, but their shapes can still be detected by sonar. Abyssal hills give the deep ocean floor a gently wrinkled surface, rather than a perfectly smooth one. Their pattern can preserve information about spreading rates, plate movement, and the conditions under which the crust formed. Although they rarely receive the attention given to trenches or ridges, their quiet abundance matters. They are the background texture of the deep sea floor, low rises and shallow valleys repeated across immense distances. Just above the bottom, the benthic boundary layer forms a soft meeting place between water and earth. It is a thin but important zone where currents meet sediment, rocks, animals, and microbes. In this layer, particles may be lifted, carried, or settled again, depending on the strength of the flow. Oxygen and nutrients pass between seawater and the seabed, while animals feed on material moving close to the bottom. Even gentle currents can shape ripples in sand or bring food to corals and sponges on hard ground. The benthic boundary layer helps connect the solid seafloor with the moving ocean. It is not a sharp border, but a soft meeting place of water and earth. Much of deep sea life depends on what happens in this quiet layer, just above the mud and stone, where every small movement matters. Over long periods, bottom currents quietly sculpt the seafloor. These currents move along the deep ocean, guided by density, temperature, salinity, and the shape of the seabed. Where they are strong enough, they can prevent fine sediment from settling, polish exposed rock, or form ripples and waves in mud and sand. In other places, they pile sediment into long drifts called contourites, which follow the shape of continental margins or basin floors. These deposits help scientists understand ancient ocean circulation. A bottom current may be slow compared with surface waves, yet it can have lasting power because it acts for centuries and more. The deep sea floor is therefore not shaped only by gravity and falling particles. It is also shaped by water moving sideways, quietly tracing paths across the dark. Where currents move loose grains, ripples can appear in seafloor sand or mud. In shallow seas, waves often create ripples that shift with storms and tides. In deeper water, bottom currents can shape similar patterns more slowly, especially where sediment is loose enough to move. Ripples record the direction and strength of flow, giving scientists clues about recent conditions near the seabed. Some are small and delicate, while larger sediment waves can stretch across broad areas. These features may look simple, but they show that the ocean floor is touched by motion, even in places that seem calm. A ripple is a small ridge made by moving water and loose grains. On the seafloor, repeated ripples turn invisible currents into visible texture, like quiet handwriting in sand or mud, preserved until the next flow. Far from shore, deep-sea sediment may fall so slowly that a thin layer represents thousands of years. Much of it begins as tiny mineral grains, volcanic ash, wind-blown dust, or the remains of microscopic ocean life. Shells made of calcium carbonate or silica may sink after plankton die, joining the soft rain of particles often called marine snow. In some places, this material dissolves before it reaches the bottom, leaving red clay and very fine dust as the main covering. Near continents, sediment can arrive more quickly from rivers, storms, and underwater flows. Far from land, the pace is far slower and more delicate. The sediment on the ocean floor is not just mud. It is a quiet archive of climate, life, erosion, and ocean chemistry. Every layer carries a little of the world above. In some regions, calcium carbonate ooze gathers where tiny shells survive the descent. These shells often come from microscopic plankton, such as foraminifera and coccolithophores, that live in the upper ocean. After they die, their remains may sink and gather as pale sediment on the seabed. This kind of ooze is common where the water is not too deep for calcium carbonate to dissolve before burial. Over long periods, it can become limestone or chalk if compressed and hardened. The presence of carbonate ooze depends on surface life, water chemistry, depth, and the rate of sediment supply. It connects bright plankton blooms with dark seafloor deposits. A soft layer of pale mud can be the settled memory of countless tiny shells that once drifted in sunlit water. Elsewhere, siliceous ooze forms from the remains of organisms with glass-like shells. Diatoms and radiolarians are two important sources of these delicate shells, which can survive sinking if conditions allow. Siliceous ooze is more common in areas of high biological productivity, especially where nutrient-rich waters support many plankton. It may occur in parts of the Southern Ocean, the North Pacific, and equatorial upwelling regions. Unlike carbonate shells, silica has its own patterns of dissolution and preservation. So the distribution of silicified sediment tells scientists about ocean conditions under a microscope. These deposits can contain intricate shapes, spines, lattices, and glassy forms. The mud itself may look plain, but it carries a hidden beauty. On the seafloor, countless small skeletons can make a soft archive of ocean life. The carbonate compensation depth is the chemical level, where calcium carbonate dissolves faster than it can accumulate. Above this depth, the shells of many tiny organisms can reach the seafloor and remain in sediment. Below it, colder water, higher pressure, and water chemistry make calcium carbonate less stable, so shells tend to dissolve before they can build thick deposits. The exact depth varies among ocean basins because temperature, circulation, and chemistry differ. This boundary helps explain why some deep seafloor areas are covered in pale carbonate ooze, while others hold red clay or siliceous material. It is not a sharp, solid line, but a broad chemical threshold in the deep ocean. The carbonate compensation depth shows that the seafloor surface depends not only on what falls from above, but on what survives the descent. The lysocline marks a shallower zone where calcium carbonate begins dissolving more quickly in seawater. It lies above the carbonate compensation depth, where carbonate accumulation becomes very difficult. Across the lysocline, tiny shells made of calcium carbonate may look increasingly etched, thinned, or broken as they sink or rest on the seabed. Its depth varies with ocean chemistry, temperature, pressure, and circulation. The lysocline helps scientists understand why carbonate sediments are common on some parts of the seafloor and scarce in others. It also makes deep-sea mud sensitive to changes in ocean chemistry through time. The boundary is not a wall, but a gradual chemical transition. It shows that the ocean floor is shaped by dissolution as well as deposition, with some shells fading back into seawater before they can become lasting sediment. In remote basins, red clay can gather at one of the slowest sedimentation rates on Earth. It is common in remote parts of the ocean, far from continents and away from the richest plankton blooms. The clay may include wind-blown dust, volcanic ash, tiny mineral particles, and material left after other shells dissolve. Because very little sediment arrives in these regions, the surface can take an extremely long time to build even a small thickness. Red clay can contain cosmic dust, fish teeth, and other rare particles that would be diluted in faster-growing deposits. Its color often comes from iron-bearing minerals. To the eye, it may seem like simple mud, but it represents an unusually slow kind of time. On these distant plains, the ocean floor gathers the faintest traces of earth, air, sea, and space. By collecting sediment cores, scientists can read the seafloor's history layer by layer. A core is collected by pushing or drilling a tube into the seabed and bringing up a column of sediment. The youngest material is usually near the top, while older layers lie deeper. By studying fossils, chemistry, grain size, and magnetic signals, researchers can learn about past climates, ocean circulation, volcanic eruptions, and biological changes. Some cores preserve records stretching back millions of years, especially in places where sediment has accumulated steadily. They are not perfect books because currents, burrowing animals, and gaps can disturb the record. Even so, they are among the most valuable archives on Earth. A seafloor core turns dark mud into a timeline, holding quiet evidence of worlds that have already passed. Through ocean drilling, researchers have revealed a deeper layered story beneath the seabed. Research ships can lower long drill strings through kilometers of water and recover cores from sediment and rock below. These cores reveal the age of ocean crust, the chemistry of ancient seawater, the movement of plates, and the lives of microscopic organisms that once floated above. Drilling is difficult because the ship must stay almost perfectly positioned while waves, wind, and currents move around it. Yet the samples brought up from the seabed have transformed Earth science. They helped confirm that oceanic crust grows at ridges and becomes older away from them. They also show how sediment slowly records climate and biological change. A drill core from the ocean floor is a narrow column, but it can open a deep view into planetary time. Over geologic time, the burial of carbon in seafloor sediment becomes part of Earth's long carbon cycle. Organic matter from surface life sinks through the water, and a small fraction escapes decay long enough to be buried in sediment. Carbonate shells can also become part of seafloor deposits, where conditions allow them to survive. Once buried, this carbon may remain locked away for long periods, especially if sediment continues to accumulate above it. The amount preserved depends on oxygen, temperature, depth, productivity, and burial rate. Most organic matter is recycled before deep burial, but the small portion that remains matters over geologic time. The ocean floor is therefore not only a place where particles settle, it is one of Earth's slow storage systems, holding traces of former life in layers of mud, shell, and mineral grains. Under a microscope, deep-sea fossils can reveal how ancient oceans changed. tiny shells from foraminifera, coccolithophores, diatoms, and radiolarians can accumulate in layers after the organisms die. By studying their shapes, species, and chemical composition, scientists can infer past water temperatures, ice volume, nutrient conditions, and circulation patterns. Oxygen isotopes in some shells are especially useful for reconstructing glacial and interglacial cycles. These fossils are small, but they are often abundant enough to form clear records through time. Sediment cores from the seafloor have therefore become essential archives for understanding climate history. A grain of deep-sea mud may contain many remains too small to see with the unaided eye. Under a microscope, those remains become quiet witnesses of changing seas, preserving signals from waters that moved across Earth long ago. Across the planet, mid-ocean ridges form the longest mountain system on Earth. These ridges run through the major ocean basins, winding for tens of thousands of kilometers as places where tectonic plates move apart. At their centers, molten rock rises from below, cools in seawater, and becomes new oceanic crust. The ridge system is not one single smooth line, but a broken chain of high ground, valleys, faults, and volcanic features. Some parts rise high enough to form islands, while most remain hidden beneath deep water. Earthquakes and small eruptions occur there as the crust stretches and opens. Mid-ocean ridges remind us that the seafloor is not only a surface that receives sediment. It is a place where Earth actively creates new rock, slowly widening ocean basins from within, one cooled flow at a time. At spreading centers, new ocean floor is born as tectonic plates move apart. At spreading centers, hot material from the mantle rises and partly melts as pressure decreases. The molten rock reaches the seafloor or cools below it, forming basalt, a dark volcanic rock common in oceanic crust. As fresh crust forms, older crust is pushed away on both sides, like a very slow-moving belt. Magnetic minerals in the cooling rock record the direction of Earth's magnetic field at the time they formed, creating striped patterns on the sea floor. These stripes help scientists confirm plate tectonics in the 20th century. The floor of the ocean carries a slow, steady record of Earth's moving outer shell. It is a memory written in stone and magnetism, preserved across the dark seabed through immense spans of time. Beneath the sediment, oceanic crust has a layered structure made from volcanic rock and cooled magma. At the top, there may be sediment, followed by basalt flows that erupted onto the sea floor. Below that, vertical sheets of rock called dikes record pathways, where magma once rose toward the surface. Deeper still, gabbro forms from magma that cools slowly beneath the crust. Together, these layers make oceanic crust thinner and denser than most continental crust. Scientists know this structure from drilling, seismic studies, and places on land where old seafloor has been lifted and exposed. The layers reveal how a spreading ridge works from the inside outward. Oceanic crust may seem like a single dark floor, but it is really a cooled system of eruptions, cracks, and chambers, arranged in quiet order below the seabed. When lava erupts into cold seawater, pillow shapes can form almost instantly. The outer surface of each flow chills quickly, forming a dark crust while the inside remains hot and soft for a short time. As more lava pushes forward, it creates rounded bulbous shapes that look like stacked pillows. These formations are common at mid-ocean ridges and undersea volcanoes. Pillow lavas are useful clues because they show that basalt erupted underwater, even when ancient examples are later found on land after tectonic uplift. Their shapes preserve the meeting of fire and water in a simple, visible form. The rapid cooling does not stop the seafloor from growing. It gives new crust its first texture. A pillow lava field is a frozen record of eruption in the deep sea. As basalt cools at ridges, it can record reversals of Earth's magnetic field. When lava cools at a mid-ocean ridge, magnetic minerals inside it align with the direction of the planet's magnetic field at that time. Earth's magnetic field has reversed many times, so newer crust preserves different magnetic directions in a striped pattern on either side of spreading ridges. These mirror-like stripes were a major piece of evidence for seafloor spreading and plate tectonics. They showed that ocean crust forms at ridges and moves outward, carrying a time record with it. The pattern is not visible to the eye on the dark seabed. It is detected with magnetic instruments. Still, it is one of the clearest hidden writings on Earth, a slow barcode of motion and reversal beneath the ocean. Compared with many continental rocks, oceanic crust is usually young because it is continually recycled. New crust forms at mid-ocean ridges, then travels outward for millions of years as part of a moving plate. As it cools, it becomes denser and sinks slightly lower into the mantle, which is why older seafloor usually lies deeper than younger seafloor. Eventually, much oceanic crust reaches a subduction zone, where it bends down beneath a neighboring plate and returns into Earth's interior. This cycle means that the seafloor is generally not as ancient as many rocks found on land. Continents can preserve very old crust, while ocean basins are renewed again and again. The ocean floor is a restless surface in slow motion, created, cooled, carried, and sometimes drawn back into the planet, completing a vast geologic circuit. Near young ridges, heat flow through the ocean floor is at its highest. Fresh oceanic crust forms hot, then cools as it moves away from the ridge and grows older. Scientists measure heat flow by placing probes into the sediment and recording how temperature changes with depth. These measurements show how Earth loses internal heat through the seafloor. Near ridges, heat escapes quickly through young fractured crust, often helped by hydrothermal circulation. Farther away, older crust is cooler, thicker, and usually buried by more sediment, so heat flow is lower and steadier. This pattern supports the idea of moving plates and renewing ocean basins. The ocean floor is not equally warm everywhere. Its temperature beneath the mud carries a memory of when the crust was born and how long it has traveled. Where plates separate slowly, spreading ridges often develop deep central valleys. Where plates pull apart slowly, the crust can stretch and break, forming a rift valley bordered by rugged fault scarps. Volcanic activity still creates new seafloor, but faulting is especially important in shaping the terrain. These ridge valleys can hold lava flows, hydrothermal vents, loose rocks, and steep walls that expose deeper parts of the crust. The Mid-Atlantic Ridge is a well-known example of a slow-spreading ridge with a prominent central rift in many areas. Its landscape is rougher than many fast-spreading ridge crests. The shape of a spreading ridge depends on how quickly plates move, how much magma arrives, and how the crust responds. A slow ridge is a place where the seafloor opens with visible tension, forming a long valley in the deep. Where plates separate more quickly, ridge crests tend to look smoother and broader. Where plates separate more quickly and magma supply is steady, new crust can form in a more continuous way. Instead of a deep central valley, The ridge crest may have a broad rise with smaller faults and volcanic features. This does not make it simple or inactive, because eruptions, cracks, and hydrothermal systems still occur there. It means the balance between magma building and fault stretching is different. The East Pacific Rise is a major example, with sections that spread rapidly compared with the Mid-Atlantic Ridge. Studying these differences helps scientists understand how new ocean floor is constructed under different conditions. The seafloor does not grow with one repeated shape. Its birthplace changes character with the pace of plate motion and the supply of molten rock. Across the deep basins, fracture zones remain as long scars from plate movement. They often extend away from mid-ocean ridges, marking places where different sections of crust once slid past each other at transform faults. Even after the active boundary moves away, the old line remains visible as a difference in seafloor depth, age, and structure. Fracture zones can cross ocean basins for thousands of kilometers, forming straight or gently curving features on maps. They help scientists trace how plates have moved through time, because crust on one side may be older and cooler than crust on the other. The seabed can stand at different levels across the zone. A fracture zone is not just a crack. It is a long memory of sideways motion, drawn into the deep floor of the sea. At transform faults, offset ridge segments slide past one another horizontally. At these faults, plates slide past each other horizontally, connecting sections of spreading ridge that do not line up in a single continuous line. Earthquakes can occur along active transform faults as the crust moves. These faults help accommodate the curved motion of plates over Earth's round surface. On maps, they often appear as straight breaks cutting across ridge segments, giving the ridge system a stepped pattern. The seafloor near them can be rugged, with steep walls, valleys, and exposed rock. Transform faults show that seafloor spreading is not a simple straight opening. It is a linked system of spreading centers and sliding boundaries. In the darkness below, the crust adjusts carefully to the geometry of a moving planet. In some places, oceanic core complexes expose rocks normally hidden deep beneath the crust. These features form where large faults lift and uncover rocks that usually remain beneath the upper crust. Their surfaces can appear as broad, rounded ridges marked by grooves and striations from fault movement. Instead of seeing only basalt erupted at the surface, scientists may find gabbro or mantle rocks altered by seawater. Oceanic core complexes are especially associated with slow-spreading ridges, where magma supply may be uneven and faulting can dominate. They give researchers a rare view into parts of the oceanic lithosphere that are normally hidden. A core complex is like a window open through the seafloor's outer skin. It reveals that the deep ocean crust is not always covered neatly, but can be peeled back by tectonic motion. On land, ophiolites preserve rare slices of ancient ocean floor lifted into daylight. They form when slices of oceanic crust and upper mantle are pushed onto continents or island arcs instead of being fully subducted. In an ophiolite, geologists may find rocks that match the layered structure of seafloor. Deep mantle rocks, gabbro, sheeted dikes, pillow lavas, and seafloor sediment. These rare exposures let scientists walk across materials that originally formed underwater. Ophiolites have helped researchers understand mid-ocean ridges, oceanic crust, and plate tectonics, especially before direct deep drilling and modern seafloor mapping became common. They also show that ocean floor can leave the ocean entirely through tectonic force. An ophiolite is a lifted memory of a vanished basin. a fragment of deep seabed carried into daylight and preserved among mountains. At subduction zones, deep trenches mark where oceanic plates bend downward. They form mostly at subduction zones, where one tectonic plate bends and sinks beneath a neighboring plate. From above, a trench can look like a long, narrow curve along the edge of an ocean basin. These places are often linked with earthquakes, volcanic arcs, and intense deformation of the seabed. The slope into a trench may include folded sediment, fractured crust, and steep walls shaped by plate movement. Although trenches occupy only a small part of the seafloor, they hold some of its deepest environments. Their darkness and pressure are extreme, but they are not lifeless. Trenches are deep seams in Earth's surface, marking where the planet slowly recycles its outer shell. They make the ocean floor feel both vast and folded. In the Western Pacific, the Mariana Trench holds the deepest known point in the ocean. This point, called Challenger Deep, lies in the Western Pacific, far below the surface in a curved trench system. Its exact measured depth varies slightly among surveys because measurement methods and seafloor shape are complex, but it is nearly 11 kilometers, or about 7 miles deep. At that depth, pressure is more than 1,000 times greater than at sea level. Very few vehicles have reached the bottom, and each visit is difficult because equipment must endure darkness, cold, and immense compression. The depth of Challenger Deep gives the ocean floor a powerful sense of scale. It reaches farther downward than Mount Everest rises above sea level. The deepest seafloor is a place of quiet extremes, measured with care and humility. In trench systems, hadal zones form the ocean's deepest habitats. The name comes from Hades, the ancient Greek underworld, and it usually refers to depths below about 6,000 meters, or nearly 20,000 feet. These places are not broad open plains, but narrow, deep habitats with steep sides and unusual conditions. Food is limited, pressure is enormous, and the water is cold, yet life has adapted there in careful ways. Some animals are small, soft-bodied, or specially built to function under pressure that would damage ordinary cells and structures. Microbes live there too, taking part in chemical cycles in the sediment. The hadal seafloor is remote, but it remains connected to the larger ocean through falling particles, currents, and geology. Even the deepest trenches are part of the whole sea. Near some trenches, accretionary wedges grow as sediment is scraped from a sinking plate. At some subduction zones, the top layers of mud, sand, and broken rock do not all descend into the mantle. Instead, they are compressed against the edge of the overriding plate, forming a thick wedge of folded and faulted material. These wedges can build broad ridges on the seafloor near trenches. Their layers may be squeezed, tilted, and repeated as plate motion continues. In some places, fluids escape through the wedge, influencing minerals, microbes, and the strength of the sediment. Accretionary wedges show that trenches are not only deep cuts, but active construction zones. The ocean floor there is pressed, stacked, and reshaped slowly, as if the edge of a continent were gathering a rumpled blanket from the moving sea. As old seafloor descends, water-rich minerals can carry part of the ocean into Earth's interior. As oceanic crust ages, seawater alters its rocks, and sediment collects on top of it. Some minerals formed or changed by this process contain water within their structure. When the plate sinks at a trench, it brings this material downward. As pressure and temperature rise, water can be released from minerals and move into the overlying mantle. This helps generate melting that feeds volcanic arcs above many subduction zones. The process links the seafloor with volcanoes, earthquakes, and the deep water cycle of the planet. The water involved is not a simple ocean flowing underground, but water bound inside minerals and pores. The ocean floor therefore carries part of the sea into the earth, quietly connecting surface water with deep rock. At other margins, subduction erosion slowly removes material from the underside of the overriding plate. At some margins, instead of building a large accretionary wedge, the sinking plate scrapes away pieces of the plate above it. Sediment, rock, and fragments of the forearc may be dragged downward over long periods. This process can cause the seafloor near the trench to subside or shift landward, changing the shape of the margin. It is one reason subduction zones differ so much from one another. Some build outward by gathering sediment, while others wear away the edge of the overriding plate. Subduction erosion is difficult to observe directly because it happens beneath thick water and buried layers. Still, its effects can be read in seafloor shape, drilling results, and seismic images. The ocean floor there is slowly consumed from below. During undersea earthquakes, faults can shift the seabed in a sudden moment. Along subduction zones and transform faults, stored stress may be released suddenly, causing the seabed to rise, drop, or slide sideways. These movements can leave scarps, cracks, uplifted ridges, or disturbed sediment on the seafloor. In some cases, vertical movement of the seabed can displace water above it and create a tsunami, though not every undersea earthquake does so. Scientists study seafloor earthquake traces with sonar, pressure sensors, and instruments placed on the bottom. These observations help reveal how plate boundaries behave beneath the ocean. An earthquake is brief, but its marks can remain. On the seafloor, a moment of motion may become a step in the landscape, preserved in mud, rock, and faulted ground. Rising from deep basins, seamounts are underwater mountains that reshape currents and habitats. Many are extinct or dormant volcanoes that never reach the surface, while others are part of volcanic chains across moving plates. A large seamount can stand thousands of meters above the surrounding seabed, creating a strong change in local currents and habitats. Water flowing around the seamount can lift nutrients and concentrate drifting life, which may attract fish, corals, sponges, and many deep-sea animals. The rocky slopes give creatures places to attach, hide, and feed. Because seamounts are isolated high points in wide basins, they can act like islands in the deep sea. Their hidden peaks break the flatness of the ocean floor and create pockets of life in open water. Each one changes the rhythm of the surrounding sea. After some volcanic islands sink, their wave-cut tops remain as flat-topped guyots. A volcano may rise from the seafloor until waves can erode its top near sea level. Over time, if the volcano becomes inactive and the oceanic plate cools and sinks, the island may descend below the surface. What remains is a broad, flattened summit under deep water. Guyot are important because they record a history of uplift, erosion, sinking, and plate movement. Their flat tops show that waves once worked on them in shallow conditions, even if they now lie far below the sea. A guyot is a quiet reminder that parts of the ocean floor have moved through very different worlds, from volcanic island to submerged mountain. Its shape preserves an old meeting with waves, sunlight, and shallow water. Over hotspots, volcanic island chains can trace the movement of plates across the seafloor. A hotspot is a long-lived area of upwelling heat where magma can break through a moving oceanic plate. As the plate moves, older volcanoes are carried away from the active source, while newer volcanoes form closer to it. Over time, this can create a chain of seamounts and islands with a general age pattern. Some volcanoes rise above sea level, while others remain underwater or sink after becoming inactive. Their shapes can be altered by erosion, reef growth, and substance. These chains help scientists estimate plate motion and understand mantle processes. On the seafloor, a hotspot trail is like a dotted line of cooled fire, marking where the moving crust passed over a steady source below. In long chains, quotes preserve the memory of islands that once stood in sunlight. A single quote can show an old wave-cut surface, but a chain of them can reveal the path of a plate across a volcanic source. The flat tops may lie at different depths because of age, cooling, subsidence, and later changes in sea level. Sediment and reef material can accumulate on their summits, while their slopes may host deep-sea animals on exposed rock. By studying their shapes and rocks, scientists can piece together former island stages that are no longer visible above water. A geode chain is a seafloor memory of many vanished islands. What remains are quiet, flattened summits under deep water, arranged like stepping stones across the basin, each one lowered slowly from a brighter world. From hidden eruptions, submarine volcanoes can build entire landscapes on the ocean floor. Many occur along mid-ocean ridges, island arcs, and hotspots where molten rock reaches the seabed. Some erupt quietly with lava flows, while others can produce fragmented volcanic material depending on depth, gas, and magma type. At great depth, pressure changes how eruptions behave, often limiting explosive expansion. Over time, repeated eruptions can create cones, ridges, domes, calderas, and rough lava fields. Some submarine volcanoes rise high enough to become islands, while many remain hidden as seamounts. They provide fresh rock for microbes and animals to colonize, especially where hydrothermal activity is present. A submarine volcano is a builder in darkness, adding new shape to the ocean floor through fire cooled instantly by the surrounding sea, layer after layer, flow after flow. Behind some volcanic arcs, back arc basins open where the seafloor stretches. They are often linked to subduction zones where one plate sinks beneath another and helps generate volcanic activity above. In some settings, the region behind the arc pulls apart, allowing new oceanic crust to form in a smaller basin. These basins can contain spreading centers, hydrothermal vents, young volcanic rocks, and thick sediment from nearby islands. Their geology is complex because compression, extension, melting, and sedimentation may all occur close together. Back arc basins show that plate boundaries are not single simple lines. They can create broad zones of motion and change, with the ocean floor opening even near places where another plate is sinking. In these basins, the seafloor records a delicate balance of pulling, melting, and burial. Within underwater volcanoes, calderas can form when the summit collapses after eruptions or magma withdrawal. A caldera is a broad depression, often with steep walls or a ring-like shape, created when the support beneath part of a volcano is reduced. Underwater calderas can occur on island arcs, seamounts, and volcanic ridges. Their floors may contain lava flows, domes, sediment, hydrothermal vents, and mineral deposits. Because they are below water, their eruptions and collapses are harder to observe directly than those on land. Sonar maps and deep-sea vehicles reveal their structure after the fact, showing hidden basins within volcanic mountains. A submarine caldera is a quiet hollow made by volcanic change. It shows that the ocean floor can sink inward as well as rise upward, leaving a bowl-shaped record of activity below the waves. Around warm tropical seas, atolls reveal a long link between coral growth and sinking volcanic foundations. A volcanic island may first rise from the ocean floor, then become fringed by coral reefs in warm, shallow water. As the volcanic foundation cools, erodes, and slowly subsides, coral growth can keep the reef near the sunlit surface. Eventually, the central island may disappear below the sea, leaving a ring-shaped reef around a lagoon. Beneath the living reef lies a thick structure tied to an older volcanic mountain. This idea helped early geologists understand how biological growth and seafloor sinking could work together. An atoll is not only a surface ring of coral, it is the upper sign of a much deeper story. Far below, the ocean floor holds the volcanic root of the island that came before. Near volcanic and tectonic activity, hydrothermal vents release hot, mineral-rich water from the seabed. They usually occur near volcanically active areas, especially along mid-ocean ridges, where seawater can seep down through cracks in young crust. As the water descends, it is heated by hot rock and reacts chemically with minerals underground. It then rises again, carrying dissolved metals and other substances back into the ocean. When this hot fluid meets cold deep seawater, minerals can form clouds, chimneys, and deposits around the vent. Hydrothermal vents were first observed in the deep ocean in the late 20th century, changing ideas about where life could flourish. They show that energy on the ocean floor can come from Earth's heat, not only from sunlight above. A vent is a warm opening in a dark world. Beneath young crust, hydrothermal circulation changes both rock and seawater. Seawater enters cracks in young, hot crust near spreading centers, moves through rock, warms, reacts chemically, and returns to the ocean. During this journey, the water can remove some elements and add others, altering both the crust and the chemistry of seawater. This circulation helps transfer heat from Earth's interior into the ocean. It can continue at lower temperatures long after crust has moved away from the ridge. The process is important because the ocean floor is not sealed from the water above it. Instead, young crust can act as a vast, fractured plumbing system. Hydrothermal circulation shows that rock and seawater are in slow conversation beneath the seabed, exchanging heat and minerals through hidden pathways. At some vents, black smokers release dark clouds of mineral particles into cold, deep water. Their name comes from the way the hot vent fluid looks as it meets cold seawater and forms tiny grains of metal sulfide minerals. These particles can make the water look like smoke, though nothing is burning. Around some black smokers, mineral chimneys grow as dissolved substances solidify layer by layer. The fluid can be extremely hot, yet the crushing pressure at depth allows it to remain a dense fluid instead of simply boiling away. Near these vents, life forms dense communities based on chemosynthesis, a process in which microbes use chemical energy instead of sunlight. Black smokers reveal a striking kind of deep-sea abundance, built around heat, minerals, and slow reactions in darkness. Their tall chimneys can rise like quiet towers on the seabed. In other places, white smokers release paler mineral fluids with a softer appearance. Their pale clouds may contain minerals such as barium, calcium, and silicon compounds, depending on the local chemistry of rock and water. They are often cooler than the hottest black smokers, though they can still be very warm compared with surrounding deep seawater. White smoker chimneys may grow into delicate towers, flanges, and terraces where mineral-rich fluid meets cold water. Like other vents, they can support microbes that use chemical energy, along with animals connected to those microbial communities. Their lighter color comes from the kinds of particles forming as the vent fluid mixes with seawater. A white smoker is a softer-looking expression of the same deep process. Seawater entering hot crust, changing underground, and returning transformed to the ocean floor. When seawater reacts with mantle rocks, serpentinization can transform the chemistry below the seabed. It happens when seawater reacts with certain mantle rocks, especially rocks rich in the mineral olivine. This reaction forms new minerals, produces heat, and can release hydrogen, a gas that some microbes may use as an energy source. Serpentinization is important near slow-spreading ridges and places where deep rocks are exposed to seawater through faults. It can create unusual seafloor environments, including alkaline vents with pale mineral structures. The process shows that the ocean floor is not only shaped by heat from magma, but by chemistry between rock and water. Deep beneath the seabed, seawater can help transform the planet's interior materials. A hidden reaction in dark stone can become part of the living and chemical rhythm of the sea. At alkaline vent fields, pale mineral towers can grow from reactions between seawater and deep rock. One well-known example is the Lost City hydrothermal field in the Atlantic Ocean, where warm, alkaline fluids rise through structures rich in carbonate minerals. These vents differ from many black smokers because they are not driven mainly by fresh volcanic eruptions. They are closely linked to serpentinization, the reaction between seawater and mantle rocks. Their fluids can contain hydrogen and methane, making them interesting to scientists studying chemical energy and the possible conditions for early life. The towers can look pale and sculpted against the dark sea floor. An alkaline vent field shows that hydrothermal activity has more than one form. It can appear as a mineral garden built by water, rock, heat, and chemistry working slowly together. Without sunlight, chemosynthesis lets some deep sea communities build food from chemical energy. At hydrothermal vents and some other seafloor habitats, microbes use chemicals such as hydrogen sulfide or methane as an energy source. These microbes form the base of food webs that can support tube worms, clams, mussels, shrimp, crabs, and many smaller organisms. The animals themselves are not magically independent of the wider ocean, but their communities rely strongly on chemical energy rising from below. In some species, microbes live inside animal tissues, sharing nutrients in close partnership. This discovery widened the idea of what an ecosystem could be. The ocean floor is not only a place where food falls from above. In rare places, it is where food begins. Darkness there can still hold a living source, steady, unexpected, and beautifully practical. Around vent systems, seafloor massive sulfide deposits can grow from metal-rich fluids. When hot vent fluids rise through oceanic crust, they can carry dissolved metals such as copper, zinc, iron, and other elements. As the fluids mix with cold seawater, minerals precipitate and build chimneys, mounds, and layers on or beneath the seabed. Over time, an active vent field can create a deposit of metal-rich sulfide minerals. These deposits help scientists understand how ore bodies may have formed in ancient oceans. Similar rocks are now found on land where old seafloor has been uplifted and altered. At the seafloor, The deposits are also part of living vent habitats, so they are more than mineral piles. They are places where geology, chemistry, and biology meet, built by hot water moving through dark volcanic ground. Along continental margins, cold seeps release methane, sulfide-rich fluids, or other chemicals more gently. Unlike hydrothermal vents, they are not mainly defined by very hot water. They can occur along continental margins, near faults, or where buried organic material breaks down under sediment. Cold seep communities may include mussels, clams, tube worms, microbes, and carbonate rocks formed by chemical reactions. Many of these organisms depend on microbes that use chemical energy, making cold seeps part of the wider story of life without sunlight. Some seeps release methane bubbles into the water, while others are gentle and less visible. Cold seeps show that the ocean floor breathes chemically in more than one way, with slow leaks that support patient, specialized life. Their activity can last far longer than a single vent eruption. In cold, high-pressure sediment, methane hydrates can store gas in an ice-like solid. They form when methane and water combine under high pressure and low temperature, creating a solid that looks somewhat like pale ice, but contains trapped gas. Large hydrate deposits occur along some continental margins, where organic matter buried in sediment breaks down and releases methane. These deposits are part of Earth's carbon system, because methane is a powerful greenhouse gas if it reaches the atmosphere. Most seafloor hydrates remain stable in their pressure and temperature conditions, locked beneath the seabed or near it. Scientists study them with care because they connect geology, climate, microbes, and the stability of underwater slopes. Methane hydrates show how the ocean floor can store invisible material in a solid form. Beneath soft mud, a quiet chemical structure may hold ancient carbon. From some muddy places, gas bubbles rise in steady streams from the seabed. These bubbles often contain methane, though their exact source can vary from place to place. Some come from buried organic matter that microbes have broken down, while others may be linked to deeper geological processes. When bubbles escape from the sediment, they can feed microbes and create small local ecosystems near the seabed. In cold water and high pressure, some bubbles may even form thin hydrate skins as they rise. Acoustic instruments can detect bubble plumes because gas reflects sound differently from seawater. To scientists, a plume is not just a trail of bubbles. It is a sign of movement between the buried floor and the ocean above. A simple stream from the mud can reveal hidden chemistry below. Under pressure, below soft sediment, mud volcanoes can push water, gas, and mud upward. They are not volcanoes in the usual fiery sense, because they do not erupt molten rock. Instead, they release mixtures of mud, water, gas, and sometimes fragments from deeper layers. Mud volcanoes can form on continental margins, in subduction zones, and in other places where pressure builds inside buried sediment. Some are small mounds, while others create broad features across the seabed. The fluids they release can carry methane and other chemicals that support specialized microbes and animals. Their shapes may change as new mud flows spread over older surfaces. A mud volcano is a gentle-looking sign of pressure below. It shows that even soft sediment can move upward, carrying the deep seabed's hidden chemistry to the surface. Where fluids escape, pockmarks may appear as shallow craters in soft seafloor sediment. They can appear as round or oval depressions in soft sediment, sometimes grouped in large fields. Many form when methane, water, or other fluids move upward through the seabed and disturb the surface. Some pockmarks are active, with ongoing seepage, while others are old marks left from past escape. They can vary greatly in size, from small hollows to features wide enough to appear clearly on sonar maps. Pockmarks matter because they reveal pathways connecting buried layers with the ocean above. They may also influence local habitats by changing sediment texture and chemistry. To a passing camera, a pockmark may seem like a simple dip in the mud. To scientists, it is a quiet footprint of something that rose from below. In certain basins, brine pools rest on the seabed like lakes within the ocean. They form where very salty water collects in depressions, often near places with buried salt deposits or active seepage. Because brine is denser than normal seawater, it can sit as a separate layer with a visible surface, almost like a shoreline under the sea. Some brine pools contain little or no oxygen and can be harsh for many animals, but microbes and specialized communities may live around their edges. Mussels, shrimp, and other organisms can gather where chemical energy is available. The boundary between seawater and brine can look strangely still, even though it is deep below the ocean surface. A brine pool shows that the seafloor can hold hidden bodies all of water within water, separated by density and chemistry. Over seeps and vents, microbial mats can spread as living films on sediment or rock. These mats are made of dense communities of microbes, often appearing as pale, orange, brown, or dark films on sediment or rock. At cold seeps, hydrothermal vents, and other chemically active places, microbes may use methane, sulfide, hydrogen, or iron as energy sources. Their growth can change local chemistry and provide food for grazing animals. Mats can be thin and delicate, yet they may signal important processes below the seabed. They show scientists where fluids are emerging and where chemical energy is available. In places without sunlight, a mat can mark the surface expression of hidden reactions underground. It is a living skin on the ocean floor, spread quietly over mud or stone where chemistry rises into life. Inside the sediment itself, orthogenic minerals form directly through chemical reactions. The word means that the minerals are made in place, rather than carried there as grains from land or shells from plankton. Examples can include carbonate minerals at methane seeps, pyrite in low oxygen mud, and certain phosphate or manganese minerals under specific conditions. These minerals can record the chemistry of pore water, microbial activity, and the movement of fluids through sediment. They may grow as tiny crystals, crusts, nodules, or cement between grains. Their formation shows that sediment continues changing after it reaches the seabed. The ocean floor is not just a passive resting place for particles. It is a chemical workshop where buried water, microbes, and minerals slowly rearrange matter into new forms beneath the surface. Only a short distance below the surface, oxygen can disappear from seafloor mud. The uppermost layer may contain oxygen from seawater, allowing animals and microbes to use it for life processes. Deeper down, microbes consume oxygen as they break down organic matter, and other chemical reactions take over. This creates zones where nitrate, manganese, iron, sulfate, or methane become important in the sediment's chemistry. The depth of these zones depends on how much food reaches the bottom, how fast sediment accumulates, and how easily water moves through it. To the eye, the mud may look uniform, but chemically it can be layered like a quiet, invisible landscape. Seafloor sediment is not dead material. It is a living chemical system, where microbes shape what happens below the first few centimeters, slowly and constantly. Far beneath the seabed, microbes can live slowly inside buried sediment and rock. Some exist far below the surface of the seabed, where energy is scarce and life proceeds extremely slowly. These microbes may use chemical reactions involving hydrogen, methane, sulfate, iron, organic matter. Their activity can influence carbon, sulfur, and other element cycles over long timescales. Scientists study this deep biosphere by collecting carefully protected cores and looking for cells, DNA, and chemical signs of metabolism. Life in these places is very different from fast-growing surface life. It may involve long periods of survival, slow repair, and tiny amounts of energy. The discovery of deep subsea floor microbes changed the meaning of habitat on Earth. The ocean floor is not only a surface for life. In some places, life continues far inside it. From the sunlit ocean above, marine snow falls toward the deep sea floor. It is made of dead plankton, waste pellets, mucus, mineral grains, and other small bits drifting down from the upper ocean. Most of it is eaten, broken apart, or dissolved before reaching the bottom. But enough arrives to matter. On abyssal plains, this slow rain is one of the main food sources for animals and microbes living in sediment. Seasonal changes near the surface can even affect deep places because blooms of plankton may send more material downward later. Marine snow links sunlight, surface life, and the dark seafloor in one quiet chain. Although the deep ocean feels distant from the bright surface, its communities often depend on this soft, steady descent from above. By burrowing and feeding, many animals quietly reshape the sediment they live in. Worms, clams, sea cucumbers, small crustaceans, and other organisms burrow, crawl, feed, and stir the upper layers of mud. This process is called bioturbation, which means the mixing of sediment by living things. It changes how oxygen, nutrients, and chemicals move through the seabed. Burrows can create tiny pathways for water, while feeding trails leave patterns across the surface. Even small animals can influence large areas when their activity continues over long periods. For geologists, bioturbation can blur layers in sediment, making the record more complex but more alive. The ocean floor is not a still carpet of mud. In many places, it is slowly turned, tasted, tunneled, and refreshed by creatures working quietly just below the surface. Across wide, deep areas, sea cucumbers act as slow recyclers of seafloor mud. These soft-bodied animals move over or through sediment, taking in mud that contains organic particles and microbes. After digesting what they can use, they release cleaner sediment back to the seabed. In this way, they help process the thin food supply that reaches deep environments. Some deep-sea species are simple in shape, while others have delicate swimming forms that can lift away from the bottom for short distances. Their slow movement leaves tracks, trails, and small piles behind them. Because they can be abundant on abyssal plains, sea cucumbers influence the texture and chemistry of the seafloor. They are quiet caretakers of the deep, turning scattered particles into nourishment and leaving the floor subtly changed. On rocky slopes, deep-sea corals can build delicate habitats without sunlight. Unlike tropical reef corals, many deep-water corals do not depend on algae living in their tissues. They catch tiny drifting food particles and small animals from the water, using delicate branches or cups to feed in darkness. These corals often grow slowly on seamounts, continental slopes, and rocky ridges where currents bring enough food. Their skeletons can create complex habitats for fish, brittle stars, worms, sponges, and other animals. Some coral structures may persist for centuries or longer, becoming records of past ocean conditions. Because they grow slowly and can be damaged easily, deep-sea coral communities are considered fragile. Their presence shows that the ocean floor can hold intricate living architecture far from sunlit reefs, shaped by patience, current, and time. In cold depths, glass sponges create fragile-looking structures from silica. Silica is the same basic material found in quartz and many kinds of sand, but in these animals it forms tiny internal supports called spicules. Some glass sponges look like cups, tubes, or woven baskets, filtering seawater for food particles. In certain cold, deep environments, sponge grounds can cover large areas and create shelter for many small animals. Their bodies may appear fragile, yet their structures are well suited to stillness, flow, and long life. Some species can grow very slowly, recording the calm pace of deep environments. Sponge habitats can be especially important, where the sea floor is otherwise soft and open. A field of glass sponges is like a quiet forest of living filters, built from mineral threads in dim water. When a whale sinks after death, its body becomes a temporary island of food. When a large whale dies and sinks, its body can deliver a rare concentration of organic matter to depths where food is usually scarce. Scavengers may arrive first, including sharks, hagfish, crabs, and other animals that feed on soft tissue. Later, worms, microbes, and smaller creatures use the bones and remaining material. In some stages, bacteria break down fats inside the bones and produce chemicals that support chemosynthetic communities. A single whalefall can influence a patch of seafloor for years, and perhaps longer, depending on size and conditions. These events help connect life near the surface with the deepest habitats below. The ocean floor receives not only fine marine snow, but occasional great gifts from the water column. Resting on deep sediment, xenophyophores show that a single cell can grow surprisingly large. Although they are only one cell, some can grow large enough to be seen easily, forming delicate structures from sediment grains and organic material. They are related to foraminifera, a group of shell-building single-celled organisms. Xenophyophores often live on abyssal plains, seamounts, and trench regions, where they may provide shelter and surface texture for tiny animals. Their bodies are fragile, so they can be difficult to collect without damage. Scientists are still learning about their diversity and ecological roles. These organisms challenge the simple idea that single-celled life must be microscopic. On the ocean floor, a single cell can become a small habitat, a soft structure resting quietly in the deep, built from grains gathered out of the surrounding sediment. In the deepest trenches, hadal amphipods scavenge food that reaches the seafloor. They resemble tiny shrimp or sandhoppers, and often act as scavengers, feeding on organic material that reaches the trench floor. Their bodies are adapted to intense pressure, cold water, and limited food. Some species are found only in certain trench systems because hadal habitats are separated from one another by shallower seafloor. This isolation can make trenches like deep biological islands. Amphipods are often among the animals captured by baited landers, sent into great depths, helping scientists study life where direct observation is difficult. Their presence shows that even the deepest seafloor supports active animals. In a place of darkness and pressure, small scavengers move across sediment, turning rare food into part of a living system, grain by grain. Near trench bottoms, deep-sea snailfish show how vertebrates can adapt to extreme pressure. Some species live thousands of meters down, including in hadal zones where conditions would crush many familiar animals. Their bodies are soft, pale, and delicate, with features suited to deep pressure rather than speed or hardness. They feed on small crustaceans and other prey near the trench floor. Instead of heavy bones and strong scales, they have a flexible form that works in their environment. Scientists have filmed and collected hadal snailfish using deep-sea landers and submersibles, giving rare views of fish life near the ocean's lowest regions. These animals show that the deep floor is not limited to microbes and scavengers. Even fish can find a place there, moving softly through cold water above the trench sediment. Across some abyssal plains, manganese nodules grow layer by layer over millions of years. These nodules are rounded lumps that grow very slowly as metals gather around a small core, such as a shell fragment, tooth, or grain of rock. They often contain manganese and iron, along with smaller amounts of other metals. Nodules may rest partly buried in soft sediment across abyssal plains, especially where sediment falls slowly enough that they are not quickly covered. Their growth can take millions of years, making them some of the slowest forming features on the seafloor. They are of interest to science and industry, but the deep habitats around them are fragile and not fully understood. Each nodule is a small mineral record of patience on the ocean floor. Its surface grows layer by layer in near darkness. On exposed seamount rock, polymetallic crusts gather metals slowly from seawater. Unlike loose manganese nodules, these crusts form as thin mineral layers attached to exposed rock. They gather metals from seawater very slowly, including manganese, iron, cobalt, and other elements. Their growth is favored where currents keep sediment from covering the rock surface. Over millions of years, the crust may thicken only a small amount, creating a dark coating on old volcanic slopes. These mineral layers interest scientists because they record seawater chemistry and long-term ocean conditions. They also raise environmental questions because seamount habitats can be rich and fragile. A polymetallic crust is a patient skin on the seafloor, growing atom by atom from the surrounding water. Its dark surface may hold a record of deep currents, changing chemistry, and immense time. Because these minerals form in fragile habitats, deep-sea mining proposals raise difficult questions. Interest often centers on manganese nodules, cobalt-rich crusts, and seafloor massive sulfide deposits. These materials can contain metals used in modern technology, but they occur in habitats that may be fragile, slow to recover, and still poorly understood. Nodules, for example, can provide hard surfaces for animals in otherwise soft abyssal plains. Removing them would disturb sediment and the communities living on and around them. Scientists, governments, and environmental groups continue to study the risks, rules, and knowledge gaps involved. The issue shows that the ocean floor is not an empty storehouse. It is a living and geological environment, built over immense time. Any use of its minerals must be weighed against the quiet systems already present there. In polar regions, iceberg keelsaws can scrape long plough marks across shallow seafloor. These marks are common in some polar and formerly glaciated regions, where floating ice can scrape mud or sand as wind and currents move it. The groove may be straight, curved, or crossed by other marks, depending on the iceberg's motion. Some plough marks are recent, while others remain from times when colder climates and lower sea levels allowed ice to reach different areas. These features tell scientists about past ice movement, water depths, and changing climate conditions. The seafloor can preserve the passage of ice long after the iceberg has melted. A plough mark is a quiet scratch made by a drifting giant, a line left behind where frozen fresh water once touched the ocean bottom. When ice melts, dropstones can fall from floating ice into fine marine sediment. Glaciers and icebergs can pick up rocks from land, hold them in ice, and later drop them into the ocean as the ice melts. When a stone falls into soft mud far from land, it may stand out clearly from the surrounding fine-grained deposit. Ancient dropstones preserved in rock can show that floating ice once reached a region, helping scientists recognize past glacial conditions. They may even deform the layers beneath them as they land, leaving a small impact structure in the mud. A dropstone is a simple object with a long journey. It begins on land, travels in ice, sinks through seawater, and rests on the ocean floor as a small, heavy message from a colder world. From former ice sheets, glacial troughs can continue from land into the seabed. During ice ages, glaciers flowing from mountains or ice sheets carve deep channels through rock and sediment. Where those glaciers reach the sea, they could extend across continental shelves, shaping the seabed beneath them. After the ice retreated and sea level changed, many troughs remained underwater. Their floors may hold moraines, ridges, basins, and fine sediment left by melting ice. These submerged valleys help scientists reconstruct the size and direction of former glaciers. They can shape modern habitats and guide currents along the shelf. A glacial trough on the sea floor is the memory of moving ice, preserved beneath waves. It turns the ocean floor into part of a larger landscape that once joined mountains, ice, and sea. After sea level rises, drowned shorelines may remain preserved beneath modern waves. During colder periods of Earth's recent history, much water was locked in ice sheets, and global sea level was lower than today. Coastal plains, river valleys, dunes, and beaches then existed in places that are underwater now. As ice melted and sea level rose, these surfaces were flooded and sometimes buried by marine sediment. Sonar, diving surveys, and sediment cores can reveal old beach ridges, terraces, and channels beneath later deposits. These features show that the edge of the sea has moved many times. A drowned shoreline is not a lost story, but a preserved boundary between land and water. Beneath modern waves, the seafloor may hold the shape of an older coast, softened but still partly readable. Beneath continental shelves, ancient river channels can still cross what is now seafloor. When sea level was lower, rivers flowed across land that is now submerged, cutting valleys and carrying sediment toward the coastline of that time. After sea level rose, seawater covered those channels, and marine sediment partly filled them. Some remain visible in sonar maps or seismic images as winding forms beneath the seabed. They can help researchers understand past drainage systems, climate, and the pace of rising seas. In some places, buried channels may influence groundwater, sediment stability, or habitats on the shelf. An ancient channel under the ocean is a reminder that the seafloor can once have been dry ground. Its curves preserve the path of flowing fresh water, now resting under cold salt water and slow marine mud below. Under buried sediments, massive salt deposits can slowly reshape the seabed from below. Salt is weaker and lighter than many surrounding sediments, so when it is buried under pressure, it can slowly flow upward or sideways. This movement can create domes, ridges, faults, and small basins on the ocean floor above. In some regions, salt that formed in ancient evaporating seas now lies deeply buried beneath continental margins. As later sediment piled on top, the salt moved like very slow, thick fluid. Its motion can tilt layers, open pathways for fluids, and influence where seeps or pockmarks occur. Salt tectonics shows that not all seafloor shape comes from volcanic rock or plate edges. Some of it begins with buried minerals moving patiently under weight, lifting and lowering the seabed from within. On unstable slopes, submarine landslides can move huge amounts of sediment at once. They occur when material on a slope becomes unstable and collapses, sometimes along continental margins or volcanic island flanks. The moving mass may break apart, flow, or slide as a broad sheet across the seabed. Some ancient slides left scars and deposits so large that they can be mapped across wide areas. Causes can include rapid sediment buildup, earthquakes, gas pressure, or weakening of layers within the seabed. Although many slides happen far from human view, they can reshape slopes and create new seafloor patterns. Their deposits may bury older habitats and form uneven ground that lasts for thousands of years. A submarine landslide is one of the ocean floor's sudden changes, a rare motion in a place often defined by slowness. Even far below surface waves, benthic storms can stir the deep sea floor. These events happen when deep currents become strong enough to lift and move sediment near the bottom. They may be linked to changes in ocean circulation, tides, eddies, or flow around rough topography. A benthic storm can cloud the water with particles, reshape ripples, disturb soft deposits, and carry organic matter across the seabed. Although the deep ocean is often imagined as still, instruments have recorded episodes of strong near-bottom flow. These storms are not storms of wind and rain, but storms of current in the darkness. They help explain why some deep areas show signs of erosion or shifting sediment. The ocean floor can rest quietly for long periods, then be brushed by powerful water moving close to the ground. Near the bottom, nepheloid layers suspend fine particles in cloudy water. The particles may come from sediment stirred up by currents, material flowing down slopes, biological debris, or fine grains carried from continental margins. A bottom nepheloid layer can reduce visibility near the seabed and help transport fine material over long distances. These layers are important because they show that sediment does not only move by falling straight down, it can be lifted again, carried sideways, and settled elsewhere. Instruments that measure light scattering, particles, and currents help scientists detect them. Nepheloid layers connect the seafloor with the water just above it, forming a soft, suspended boundary. In that cloudy zone, the ocean floor is not simply receiving sediment, it is lending some of its surface back to the moving sea. To map hidden terrain, sonar turns sound echoes into images of the ocean floor. A ship can send sound pulses downward and measure how long they take to return from the seabed. Multi-beam sonar sends many beams at once, creating wide swaths of depth data as the ship moves. From these measurements, scientists build maps showing ridges, canyons, trenches, seamounts, landslides, and smaller textures. Satellites can estimate broad seafloor shape by measuring slight changes in sea surface height caused by gravity. But ship sonar gives much finer detail. Because the ocean is vast, much of the seafloor still lacks high-resolution mapping. Each new survey can reveal features never seen clearly before. sonar turns darkness into shape, allowing hidden mountains and valleys to appear as calm lines on a map, ready for study. From space, satellite altimetry can hint at large seafloor mountains through subtle gravity effects. Although satellites cannot see through seawater, they can measure tiny changes in sea surface height. A large seamount has extra mass, which slightly strengthens gravity nearby and pulls water into a gentle mound over it. A trench or low area can create a smaller opposite effect. By mapping these subtle changes across the ocean, scientists can estimate broad patterns of the seafloor. The method is less detailed than a ship's sonar, but it is valuable for remote areas where ships have not passed closely. It shows that the hidden floor influences even the ocean surface above. A mountain buried under kilometers of water can leave a faint shape overhead, quietly written not in light, but in gravity. Close to the seabed, autonomous underwater vehicles survey details ships cannot see as clearly. These machines travel through deep water on planned routes, carrying sonar, cameras, chemical sensors, and instruments that measure temperature or currents. Because they can move closer to the seabed than a ship at the surface, they can map smaller features in greater detail. Some glide slowly over plains, ridges, or volcanoes, while others follow rough terrain using careful navigation. Their work is demanding because satellite signals do not travel through seawater, so the vehicle must rely on internal systems, acoustic signals, and later corrections. When it returns, scientists can combine its data into detailed views of hidden landscapes. An autonomous vehicle is like a quiet traveler above the seafloor, gathering shapes and measurements from places no person can see directly. From a ship above, remotely operated vehicles give scientists careful eyes and hands in the deep. These vehicles are connected by long cables that carry power, commands, and video between the surface and the deep. Cameras, lights, sampling arms, and instruments allow researchers to watch vents, corals, sediment, rocks, and animals in real time. The cable can be many kilometers long, yet the vehicle may still make careful movements near fragile habitats. Operators guide it slowly to avoid disturbing soft mud or delicate life. A remotely operated vehicle can collect a rock, take a water sample, or record a close view of an animal resting on the bottom. It turns the ocean floor into an observable place, not by making it less remote, but by carrying patient eyes and careful hands into the dark. By resting quietly on the bottom, deep-sea landers let the seafloor reveal itself over time. A lander is usually a free-falling instrument frame that sinks from a ship and later returns to the surface using weights that can be released. It may carry cameras, bait, traps, pressure sensors, current meters, or chemical instruments. Because it is not attached to a long cable, it can reach very deep areas, including trenches, with less need for constant control from above. Some landers sit quietly for hours or days, recording animals that visit or measuring conditions near the sediment. Their stillness is useful because many deep-sea creatures avoid disturbance. A lander turns a patch of seabed into a small listening post. It waits in darkness, letting the ocean floor reveal its rhythms at its own slow pace. On the dark seabed, ocean bottom seismometers listen for Earth's vibrations. These instruments are placed on the seabed for weeks, months, or longer, where they listen for vibrations traveling through Earth. Because much of the planet's plate movement happens beneath the ocean, seafloor instruments are essential for understanding earthquakes, spreading ridges, transform faults, and subduction zones. On land, seismometers are easier to maintain. but they leave wide gaps over ocean basins. Instruments on the bottom help fill those gaps. Even though recovering them can be difficult, they must survive pressure, corrosion, currents, and the quiet settling of sediment. When scientists bring them back, the stored records can reveal hidden movement far below the waves. An ocean bottom seismometer is a patient listener on the dark floor, waiting for the planet's faint and sudden signals. With long-term observatories, scientists can watch deep environments change beyond a single expedition. Instead of visiting briefly with a ship or vehicle, an observatory can remain in place and collect continuous measurements. Some systems are connected to shore by cables that provide power and carry data, while others store information until they are recovered. They may measure earthquakes, temperature, currents, chemistry, sound, or biological activity. Long-term records are valuable because many seafloor processes are slow, irregular, or easily missed during short expeditions. A vent may change flow, a current may strengthen, or an animal community may shift over months and years. Observatories turn the ocean floor from a place of rare glimpses into a place of steady attention. They help reveal the deep sea as an active world with rhythms that continue whether anyone is watching or not. Across the basins, undersea cables carry much of the world's digital communication. These cables are carefully routed across shelves, slopes, abyssal plains, and around hazards such as steep canyons or unstable areas. In shallow water, they may be buried for protection, while in the deep ocean, they often rest directly on the seabed. Their paths require detailed surveys of seafloor shape, sediment, faults, currents, and human activity. Natural events such as turbidity currents, earthquakes, or submarine landslides can damage them, revealing the seafloor's ability to move suddenly. Although they are human-made, the cables show how closely modern life depends on hidden ocean landscapes. A message crossing the world may travel through glass fibers lying in darkness, stretched across plains and ridges far below the waves. Despite modern tools, high-resolution maps of the ocean floor remain incomplete. Satellites provide useful broad estimates, but detailed maps require ships, sonar, and time-consuming surveys. A vessel must pass over an area to measure it closely, and the deeper the water, the wider but less detailed each sonar footprint can become. Remote regions, rough seas, cost, and limited ship time all slow the work. International efforts continue to improve global seafloor mapping because better maps help science, navigation, hazard planning, habitat protection, and climate research. Each new survey can reveal seamounts, channels, landslides, or small features that were previously unknown. The ocean floor is not mysterious because it lacks shape. It is mysterious because its shape is hidden under depth, and careful mapping is still catching up with its scale. In the end, the seafloor is one of Earth's greatest records of slow change. It is created at ridges, carried across basins, covered with sediment, broken by faults, pierced by vents, scraped at trenches, and sometimes returned into the planet. Its surface holds traces of falling shells, drifting ice, volcanic fire, chemical seepage, buried rivers, deep currents, and living communities adapted to darkness. No single view can capture it fully, because it is both a landscape and a process. It can be smooth as an abyssal plain, rugged as a ridge valley, or narrow and deep as a trench. The seafloor teaches that Earth's most hidden places are not separate from the rest of the planet. Beneath the moving ocean, the ground itself is moving too, quietly carrying the long story of water, rock, and life. We have reached the end of our quiet journey across the ocean floor, a hidden world of plains, ridges, trenches, vents, sediments, and slow-moving stone. Beneath the waves, the seafloor is not a simple boundary at the bottom of the sea. It is a living record of Earth's deep motion, where new crust is born. Old crust is carried away, minerals gather, currents shape soft mud, and small creatures make their homes in darkness. The ocean floor reminds us that much of Earth's story unfolds far from human sight. Mountains can rise without touching the air. Valleys can stretch through black water. Warm vents can support life without sunlight. A single layer of sediment can hold traces of ancient climates, tiny shells, drifting dust, and the slow memory of worlds that came before our own. As you rest, let the thought of that deep landscape become simple and still. The ocean floor continues in darkness, patient and immense, holding its ridges, plains and trenches beneath the quiet weight of the sea. Sleep well. Good night.